All right. So, hello and welcome everyone. We are live right now. So, welcome back to this amazing platform of Tutee learning. Right? Please let me know in the live chat. Am I audible to all of you? Yeah. So, that's great. So, I can feel my own voice, right? Great. Now, welcome back to this lecture number 9 of the properties of definite integrals. And in today's class, we are not going to talk about the properties as such, but we're going to talk about two most key results. So, if you are someone who is new to this particular channel and you haven't watched the previous sessions, my utmost request to all of you, please go back to the playlist of definite integral and please watch the previous contents, right? So, without watching the previous topics, if you start watching this particular session from right now onwards, you won't be able to get something out of it, right? Alright, so in the previous topics, we have already covered something called as the gamma function, right? And before that, we have been discussing another very important result, that is the applications of inequalities in these questions of definite integral, right? And then we went on to discuss the gamma function as of the last class, right? And I remember I all asked you to solve one homework problem to all of you, right? So let me know how many of you have got the solution for this question. Please let me know how many of you got the solution for this question. Okay, so we will see how we can proceed to see how we can solve this question. But before that, if anyone have solved this question, please let me know so that I can tell you whether have done the question the right way or not. Right? Okay. So let's quickly let's quickly see the solution for this question. Right? So if you look at this problem over here, the question is basically given for the integral when the limit 0 to 1, and we have a natural log of 1 upon x and then whole to the power n minus 1, and then we have dx, right? So we have this particular function over here, right? Now if I look it carefully and if I try to do some simple modification, let us say 1 upon x be some another variable t. Okay, let us say I put 1 upon x, this particular thing, as some variable t, right? And then what I can do is that I can do the following transformation as so okay, let me put log of 1 upon x as t, right? So in this case, then if I represent x, so x will be equal to e to the power minus t, and therefore from here if I take the derivative on both the sides, so dx will be equals to minus of e to the power minus t dt. So dx will be equals to minus of e to the power minus t dt, right? So we'll have this information over here. Now, why I am doing this is very important to understand, is that I am trying to get this particular function in form of the gamma function, right? Now, why did I get this idea? The simple idea I got it because there was a power to the power n minus 1, right? So that was basically my idea, to reduce into form of exponential so that I can apply the results of the gamma function, right? Now, once I get this result, I can write this integral I going from 0 infinity to 0, right? Now, that is also another important result, to choose log of 1 upon x as some variable t, right? So, in this case, 0 to 1 interval goes from infinity to 0, right? And then we will have t to the power n minus 1, t to the power n minus 1 multiplied with minus of e to the power minus of t, right? And then we have dt over here, and then I can switch this minus sign and I can replace this with, so I can change the limits of the integral, and let us do it in this way, 0 to infinity, and then it is t to the power n minus 1 multiplied with e to the power minus of t dt, right? Now if you recall that this is nothing but the simple representation of the gamma function of n, right? So this I can write it as, it's also equals to gamma of n, right? So it is equal to gamma of n. So therefore our integral from 0 to 1, whenever I write log of 1 upon x whole to the power n minus 1 dx, now this particular integral is nothing but is simply equal to the gamma function. Okay, so this particular integral is equals to the gamma of n. Okay, this particular thing is equal to the gamma of n. Now my sole reason to give this question is basically to make you feel that gamma function is not always like this form, right? So my only motivation to give you this question is basically that whenever you see this kind of problem, you have to be curious enough to know that you have to convert that particular problem into an exponential problem so that you can think of applying the gamma function properties, right? I hope this is clear to all of you. Is this part clear to all of you? Is this part clear to all of you? Please let me know in the live chat. Is this part clear? I know this is a very simple concept, right? But still, it's a very important exercise to understand that there are certain functions which I can also represent in terms of the gamma function, right? Okay. I hope this is clear to all of you, right? So with this particular understanding, today we're going to talk about the beta function, right? So we are going to move one step ahead and we're going to try to see what is the beta function and how does a beta function looks like, right? So if I talk about beta function, so I hope you have already got this result, right? Or if you haven't got this result, I hope this explanation is clear to all of you. So let's proceed with the next topic. So the next topic we are going to discuss is the gamma function, right? So we're going to discuss about gamma function over here. Oh, sorry, we already did discuss about gamma function. We are going to discuss about beta function, right? So we are going to discuss about beta function. Okay, so we're going to discuss about the beta function, right? Now, what is the beta function and how do we write it? Generally, beta function is written like b of m comma m. So it is a two parameter function. So I have two variables m and n, which are the parameters, such that this particular integral is like 0 to 1, 0 to 1 x to the power m minus 1 multiplied with 1 minus x to the power n minus 1 dx. 1 minus x to the power n minus 1 dx, right? Where m and n are both greater than 0, where m and n are both greater than 0, right? So this, whenever I have this form of integral, this is nothing but is also called as the beta function. Okay, so this form of integral is nothing but is also called as the beta function. So whenever I talk about beta function in terms of m and n, it is simply as integral 0 to 1 x to the power m minus 1 multiplied with 1 minus x whole to the power n minus 1 dx. Okay, so this is my beta function, right? Now we're gonna look into how we can solve these problems, and along with the questions we move forward, we'll see the solution for it, right? But let's quickly observe some of the important properties that is associated with the beta function, so that when we see the question, we know how to apply it and how to get the key results, right? So therefore, if I talk about properties, of beta function. Okay, so therefore, if I talk about properties of beta function, the very first property of beta function is that beta of m comma n can also be given as beta of n comma n, right? I hope this is not an issue because you know that I can say x is equal to 1 minus t, and therefore this becomes t and this becomes 1 minus t, right? So it is not an issue, so that integral remains the same, right? So beta of m comma n is basically equals to beta of n comma m as well, right? I hope this result is clear, right? And this is true for both m and n greater than or equal to 0. Okay, the second important property is that when we have beta of m comma n, I can evaluate this beta function. Now this can be very easily proved. Okay, if you try to do it by your own, I hope you can get this particular result, that beta function of m comma n can be given as gamma of m multiplied with gamma of n whole divided by gamma of m plus n. Okay, so this is another key result that you please need to remember and please keep it in mind. Okay, these are very important and crucial result. Okay, so how to evaluate the beta function? It is solved in terms of the gamma function, right? So it is solved in terms of the gamma function. And the last property I have, that is beta of m comma n, it can also be given as 0 to infinity x to the power m minus 1 whole divided by 1 plus x whole to the power m plus n, okay, whole to the power m plus n, okay. So don't think that beta function integral will be always be of this particular form. Now if you look at a JEE Mains previous year question, the form that they gave in the exam was of this particular type. But if you also see some other questions of JEE Mains also, sometimes they also use this particular form of integral as well, okay. So that basically makes understanding clear that beta function is one of the very crucial result, especially if you look at the recent test papers, okay. So sometimes these types of questions are also being asked, right? So you don't need to worry that you need to learn about something new in this particular topic. You can obviously integrate these kinds of expression by simply using the by parts expression, right? So we have all learned how to integrate a product of two functions by using by parts, right? So if you just apply the same thing over here, you can also try to solve this beta function question over there as well, right? I hope this is clear to all of you. Please let me know if you have any questions, any queries. Okay, I'm just going through a live chat. Please let me know if you have any questions. Okay. All right. So let's see some of the crucial questions, and so that we can understand that how we are going to use this particular result to get our solution, right? So let's see one of very interesting problem. So let's quickly see one of the very interesting problem. So we have a problem over here. We have a problem over here that you have to evaluate this following integral going from 0 to 1 x to the power 6 whole multiplied with square root of 1 minus x square, square root of 1 minus x square dx, right? So we have to evaluate this integral, right? Now I know that you can try to solve this question by different methods, but ultimately you will be stuck somewhere while going on solving this question, right? Obviously you can try to think of applying the trigonometric substitution in this types of question, right? That should be your first point of attack on this question, right? So even if you try to do this question by putting, let us say you want to put x equal to cos of theta, and then you want to solve this question, that is a very useful way to solve this question. And in this case then your question goes from pi by 2 to 0. So it is basically becoming equal to cos to the power 6 theta multiplied with sine theta, right? Because 1 minus cos square theta is sine square theta, square root of that becomes sine theta, and dx become equal to minus of sine theta d theta, right? So we will have another minus sine theta d theta, right? So then, and this minus sign can be compensated with the change of the limit, and this can be given as 0 to pi by 2. Then I can have cos to the power 6 theta into sine square theta d theta, right? Now this question can be very easily solved by the Wallis theorem that I am going to discuss just after this particular topic, okay? This can be easily solved by using the Wallis formula, right? Okay, I'm going to discuss about the Wallis formula just after this topic is over, right? So this can be easily solved by using the Wallis formula, and we're gonna be solving this question just by using the Wallis formula itself as well, right? But for the time being, let's see, if I am not going to apply the Wallis formula over here, how can I still get the solution without even using this trigonometric substitution, right? So my point of view of solving this question is that there are multiple ways to get to the solution of a question. But that doesn't stop us or restricts our idea or thinking only to a particular level of idea, right? So what we're going to do over here is that once we have this particular idea clear, I can also try to approach this question as, so this same question can be given as, now whenever I see 0 to 1 integral is there and I see an irrational form of integral expression, I try to, first of all, what I can do over here, let's say I express x square as t, right? So therefore 2x dx will become equals to dt. So therefore 2x dx will become equals to dt, right? Now once I have this result, this 1 minus x square is equals to t. So and the square root of that is there. So we can write 1 minus t whole to the power 1 upon 2, and then this particular term becomes t to the power. Okay, so the one problem mistake over here, it should be 5. Okay, so sorry, this question was mentioned as 5 over here, right? So please change, this question was 5 over here, okay? In the question it was x to the power 5, right? So sorry. So therefore now we have this result, and then I can write x as t to the power 1 upon 2. So therefore x to the power 5 will become t to the power 5 upon 2, and then we will have dx. Now please note that there is 2x over here, right, which I can also incorporate. I think I am going wrong. Oh, so sorry. It is actually x to the power 6 only, right? Let me check, cross verify with the question. Yeah, it is actually x to the power 6 only. Okay, so sorry. I think it's x to the power 6 here. Yeah, so therefore, now over here it is basically t to the power 6 by 2 for this particular term. Now don't forget, you have to also substitute dx as well. So dx will become dt upon 2x. So 1 upon 2 goes out of the integral, and dt upon x will become t to the power minus 1 upon 2, right? So that x will be t to the power 1 upon 2, and 1 upon x will become t to the power minus 1 upon 2. So therefore, if you evaluate this particular term, the t to the power minus of 1 upon 2, and then we have dx, so dt over here, right? So therefore, now this integral is now converted to another form of integral, that is half times integral from 0 to 1 t to the power 5 by 2 multiplied with 1 minus t whole to the power 1 upon 2 dt, right? So therefore, this integral is now transposed to this particular form. Now if you recall, if I call this as x to the power some value m minus 1, then I can say that 1 minus x to the power n minus 1, right? So therefore, this is nothing but it is basically the beta function of 7 by 2 comma 3 by 2, because 5 by 2 I can write as 7 by 2 minus 1, and this 1 upon 2 I can write as 3 by 2 minus 1. Okay, so this is value of m, and this is the value of n, right? So therefore, this is nothing but the beta of 7 by 2 comma 3 by 2, right? Now let's quickly see how we will solve this question from here. Then this is basically half times. Now beta of this is basically given as gamma of 7 upon 2 multiplied with gamma of 3 upon 2, and then whole divided by gamma of 7 by 2 plus 3 by 2, which will become equals to 5, and we know that whenever a gamma of an integer is asked, it is basically equal to that n minus 1 factorial, right? So therefore, this particular thing will become equal to 4 factorial. Now then, I also know another important property of gamma function is that I can reduce it. So I have already learned this property, that is gamma of n plus 1 can be given as n times of gamma of n, right? So that is something what I'm going to use over here, unless and until I decode it to the lowest form, right? So I can write this as half times. Now in the numerator, this will be basically going to 5 by 2 multiplied with 3 by 2 multiplied with 1 by 2, right? And then you will be left out gamma of 1 by 2. Now there is one small result that you can always do by yourself, or you can check it, that gamma of 1 upon 2 is basically given as square root of pi. So you can try to do it by yourself. So gamma of 1 upon 2 is given as square root of pi. So this will become square root of pi. And then gamma of 3 by 2 can be given as 1 upon 2 into gamma of 1 upon 2, which is again equal to square root of pi. And the whole divided by 4 factorial over there, right? So if I evaluate this particular expression, I'm going to get the final solution equals to 5 pi upon 256. So I'm going to get the final solution to that particular integral as 5 pi upon 256. I hope this is clear, right? Is this solution clear to all of you? Arthur Vaikar, hello. Hello, sir. Yeah. Divine Gaming, hello. Is this part clear to all of you? Is this solution clear to all of you? Please let me know in the live chat. Please let me know in the live chat. Is this part or solution clear to all of you? If you have any small question, please let me know in the live chat. Or if you have any queries regarding how am I going to prepare for the special topics, for that there are special sessions, and there are basically the number is also given up. So you can find my number and my team's contact details in the live chat as well as in the description box. Okay, so please go back to the description box and find the number, and you can definitely contact us to get one-to-one connections, or if you want to get mentorship and you want to clear your doubts, you can definitely contact us on that particular number, right? But apart from that, if you have any questions regarding this particular topic itself, please let me know in the live chat so that I can entertain you. Okay. Please go over it once again. I hope this was not a difficult task. Okay. So what I did over here, I hope you are able to understand. So I am writing gamma of 7 upon 2 as, so this is n plus 1. So that is 5 by 2 plus 1. So I'm writing as 5 by 2 into gamma of 5 by 2, right? Now I can also write gamma of 5 by 2 as 3 by 2 into gamma of 3 by 2. Now similarly, I can also write gamma of 3 by 2 as 1 upon 2 into gamma of 1 upon 2, right? So this is how I reduce from one step to another, right? So this is how I am reducing step by step. Okay. So please follow up with all the properties that we have already discussed in the previous topics. And again, if you haven't watched the previous lecture, then this particular lecture is not going to be that useful to understand, right? So please go back and watch the previous lecture so that you can understand this particular topic. Okay. Now we are going to use this particular result as well. Along with that, we are going to now learn about another important formulation by which I'm going to solve this question in some few minutes, right? So let's see how we can do that as well. So now that's easiest formula to solve any integral question involving sine and cos of any integral power. Okay, when we have this power of this sine and cos term as some integers, and the limit of the integral is going from 0 to pi by 2, then we are in a position to apply the Wallis formula, right? So let's discuss about what is the Wallis formula, right? And how does it comes from? So the Wallis formula is basically derived from the recursion relation that you can always try to do while you are doing the integration by parts, right? So from that integration by parts, if you do keep on deriving the further steps and you keep on doing the recursion relation, then you will get the so-called recursion formula for integral of sine to the penny higher order derivative, right? And then once you put this limit, and then you're going to get some simplified result, that is something also known as the Wallis formula. Right. So Wallis formula, so an easy way to evaluate, so we are basically going to evaluate the integral going from 0 to pi by 2, and then we are having sine to the power mx into cos to the power nx dx, where my both m and n are belonging to an integer, Okay. Now I can and don't ask me this kinds of silly question that what happens if cos to the power m is asked and sine to the power n is asked. It is obviously understood pretty well that I can do the substitution. I can just do one transformation in King's formula, or the property of the definite integral, that is pi by 2 minus x. So a plus b minus x remains the same. Okay, so the integral of f of x or integral of f of a plus b minus x remains the same. So please try to apply that particular idea. So the result is basically as follows. Now there are two results for it. So the first result is basically m minus 1 into m minus 3 and so on up to until you get 1 or 2, or multiplied with n minus 1 into n minus 3 and so on up to until you get 1 or 2, and then whole divided by m plus n into m plus n minus of 2 and so on up to until and unless you get 1 or 2 as the continued product. And don't forget that you have to multiply with pi upon 2. Okay, so what I'm going to do is that I'm going to write this result as, as some k. Now this k is basically equals to pi by 2 if and only if my both I have both of m and n, if and only if I have both of m and n belongs to an even integer. Okay, now only when both of them are even integer, it is not like one becomes even integer, one of them is not an even integer, then can I use the result? No, both of them has to be an even integer, then only you can use the result, or k is equals to pi by 2, or it will be equals to 1 elsewhere. Okay, so in any other way it is going to be equal to 1. So depending upon what is the value of m, whether it is an even integer or not, we are going to use this result over here. So this is another very interesting result that will actually help you to simplify your life whenever you are trying to integrate any sine and cosine terms going from 0 to pi by 2. Now the question obviously comes up in your mind that what happens if I have only the sine term or only the cos term. Now I know you're very intelligent, then you can treat the one as cos to the power 0x, but then students will come up and ask for the idea that again that if I consider n as 0, then it will be minus 1, minus 3 and so on up to 1 and 2. Now whenever you get minus, you don't need to do the product. Right? So therefore this particular product won't come. So whenever cos term is not there, this product will not come. When a sin term is not there, this product will not come. So depending upon what is my need in the question, I will keep on adjusting this particular formula, right? Please let me know this formula is clear or not. Please note down this formula, very useful formula, especially for solving these kinds of integral question. Okay. Please let me know the live chat. Is this clear? Is this formulation clear to all of you? Yes or no? Is this formulation clear? Is this formulation clear to all of you? Please let me know. We'll solve questions, don't worry. But first of all, write down this formulation so that we can go on with taking up the questions. Okay. It's a very useful question and very useful topic to discuss, especially in the topic of definite integral, right? Because in questions of definite integral, you're definitely going to see some bigger integral which get reduced to this final form of cos and sine terms when you have to integrate that particular function from the limit 0 to pi by 2. And that time, if you don't know the results, you're not going to get the answers very quickly, right? So it is always very crucial. If you know the results, you can get the answer very quickly, right? And if you don't know the result, then also it's not a problem. You can always consider the things that we have already learned in indefinite integral by assuming cos square x as t, then 1 minus sine square x becomes cos square x. So those particular identity, we can use it and then we can solve it. So even if we consider sine x as t, then cos x dx will become dt, right? So we can use all those modifications that we have learned. But this is a specialized thing that I want all of you to learn now, so that when you solve questions, especially on integrals, when you have higher powers of sine and cos terms and going from 0 to pi by 2, please note that this limit has to be very important. It is only valid. It is only valid whenever the limit is going from 0 to pi by 2, or else it is not valid, right? So please, please keep this in mind, because it will be only valid when your limit is going from 0 to pi by 2. Okay. So if your limit is not going from 0 to pi by 2, sorry, you cannot apply this result, right? So I hope this is clear to all of you. So therefore, and also this is very similar to, and also this result is very similar to, I can also write the same result as gamma of m into gamma of n whole divided by gamma of m plus n. So this is nothing but the beta function. Okay, this is also a simple beta function, right? So if you also recall these particular things as well, you will be in a position to solve this question also, right? Is this clear to all of you? I think I gave there is one modification to this. This is not a exactly the beta function form. There has to be 1 2 over here, and this particular form should be gamma of m plus n plus 2. Gamma of m plus n plus 2. Okay, so this is the actual form. Okay, and there has to be some modification also. So this m is not directly equal to m. It should be uh, yeah. Okay, so I hope this result is clear, and then let's solve one question to see how we can use this particular idea to get the results very quickly, right? So if I take up one question, let us say my integral is going from 0 to pi by 2, and we have sine to the power 4x multiplied with cos to the power 6x, right? Now, if you try to do it in the traditional way, what you have learned already in the indefinite integral, you're going to see this is going to take a lot of time in solving this question, right? So in order to get quick solution for this question, we can simply use the result of the Wallis formula, and we can do this question as, so the Wallis formula says that whenever we have both m and n are integers and even integers, then the result will be multiplied by pi by 2 at the end, right? But before that, it is So whatever we have, m minus 1 into m minus 3 into m minus 5 and so on, we go on, right? So this 4 minus 1 will become equal to 3, then into 1, right? And then unless and until we get 1 or 2, we will stop. Multiplied with, so this will become 5 into 3 into 1, right? So this is the result, and then whole divided by m plus n minus m plus n into m plus n minus 2. So m plus n is 10, 10 minus 2 is 8, 8 minus 2 is 6, 6 minus 2 is 4, 4 minus 2 is 2. So unless and until I get 1 or 2, I will stop. And then this result has to be multiplied by pi by 2, and we will see this result. If we evaluate this result, this is going to be equal to 5 pi upon 256. Please try to solve this. This will be equals to 5 pi upon 256. Now, can you recall that this is exactly the same question that we already solved using the beta function over here. This is the exactly same question. Sorry, we solved it using the gamma function or the beta of this particular value, right? This is the exactly same question. Okay, so therefore, now I hope this is clear, right? So whenever we do this, so over here, we had this form, right? I think I missed some sine square theta another over here. Please check. Okay, there may be some sine to the power 4 theta over here. There has to be some sine to the power 4 theta. Okay, this sine to the power 4 theta over here, right? So you can check that this result is the same result that we evaluated right now using the Wallis formula. So using the Wallis formula, I got the same result that I was getting using the gamma function or the beta function approach, right? So therefore, now you can understand and now you can feel and see that whenever you try to whenever you can solve a same question in multiple methods as well, but knowing the Wallis formula is very crucial, because whenever you have these kinds of integral especially going from 0 to pi by 2, then this integral evaluation becomes very easy by using the Wallis formula. So that was the major key takeaway from this particular lecture over here. I hope this lecture is clear to all of you. So with this, we are wrapping up the entire course of definite integral. Now I have covered all the topics that can be done that can be studied under this particular portion of definite integral, taking in mind the syllabus is basically for our JEE Mains and Advanced examination. So in any competitive exam where your syllabus is class 11th and 12th mathematics, physics and chemistry, and where the mathematics syllabus is based upon the NCERT or curriculum or the JEE curriculum, you can definitely follow these lectures and you can prepare from these lectures, and you can also practice questions along with it so as to get perfect in it, right? So once you do all those particular exercise and you calculate and solve a lot of questions and even the previous year question, now you can see that once you do all this exercise and once you do all the practice, you will be feeling confident to solve questions, and along with that you will be able to solve the previous year question. Okay, so that was the end for the definite integrals. Now don't worry, we are going to take up question solving session up in the upcoming lectures. Okay, so for that, please stay tuned on this particular channel. Please hit the subscribe button and also click on the bell icon to never miss any upcoming notification, right? And also, along with the end of this particular topic, another very important notice for all of us is that if you are interested in studying one-to-one, where you want to get distracted free environment of studying, and you want to get specialized doubt clearance, specialized exam series, and your concepts clarity, so then you can always contact us on this number in order to get access to one-to-one batches, right? On YouTube, we are definitely learning it for free, but if you want to get scheduled classes, you want to have scheduled tech lectures, you want to have those test series, the notes, short notes, that is going to help you out further adding up help to your preparation, you can definitely contact us on this particular number and you can get access to the one-on-one live online batches. Okay, so please help us in spreading this particular awareness to among all the people around the world, right? So please share this video as much as possible among your friends, your relatives, your any one of your juniors who are basically preparing for the IIT JEE examination, even your seniors who are preparing for the competitive examination. It need not be the competitive exam, need not be the JEE or or any other engineering related exam, maybe in any other related exam where the integration topic is basically asked. So definitely you can take up all these courses to prepare for your upcoming examination and for your benefit as well. Okay, so with this take, I conclude my session over here. Thanks all of you for joining the session and for your patience as well. And with this, I wish you all the best. Please try to practice and make short notes and solve previous year questions on time to time basis. And with this, I conclude the session over here. Thank you.